The name of this video is Maxwell Inductance Legendre. In fact, in this video, we are going to continue our discussion about Maxwell's inductance, which I remind you from the previous video, is the inductance of a loop that carries a current. The loop has a radius capital A. The cross-sectional area of the wire is pi capital R squared, where again the wire is almost quasi-filiform because this capital R is much smaller than capital A, the radius of the entire loop. So in the previous video, Maxwell inductance Neumann, we found the Neumann integral associated with the mutual inductance of, instead of the self-inductance of a single loop, the mutual inductance between a large loop with radius capital A and a smaller loop above it at a distance small delta with the small loop radius being small a. So we go again, we want to go from the mutual inductance between these two distinguished loops in the limit. I make the two loops to have the same radii and very small distance between them. This mutual inductance becomes effectively the self-inductance. I remind you from the previous video that we found that the mutual inductance M21, which eventually in the limit is going to become the self-inductance, is equal, this is the solution of the Neumann integral, which again is based on first and second type elliptic integrals. And so in this case, the result is minus mu naught times the square root of capital A, the large radius, times small a, the small radius, times k minus 2 over k times the elliptic integral f of k plus 2 over k times the elliptic integral e of k. So this we found it in the previous video. All right. What are the elliptic integrals f of k and e of k? So if you look them up on, let's say, Wolfram alpha, you will find that they can be written as follows. F of k is equal to the integral from 0 to pi half in d bar phi of capital delta, to be defined in a minute, whereas e of k is given by the integral from 0, again, to pi half in d bar phi capital delta. In fact, the first one, it's 1 over capital delta. So f is the integral in d bar phi of 1 over capital delta, whereas e is capital delta. What are k and capital delta? Capital delta, theory of elliptic integrals, is given by the square root of 1 minus k squared, the sine square of bar phi, this angle here. K, I remind you from the previous video, is the modulus of the elliptic integrals, and is given in this case, in the denominator we have the square root of capital A plus small a, quantity square plus delta square. Now remind you that delta is the distance between the two planes that contain the two loops for the mutual inductance, and in the numerator we have 2 times square root of capital A times small a. This is the modulus of the elliptic integrals, 1 over delta delta, first and second type elliptic integrals respectively, E and F. Now, what do we do with these integrals? Do we compute them? Actually, instead of computing them, the ideal scenario is to expand them in a series, to use a series expansion. Now, before proceeding with the video, I want you that you go to Wolfram Alpha or Wolfram in general, you Google for the series expansion of elliptic integrals of the first and second kind. Then you pause, you look at these expansions and you meditate about them, and then you come back to this video. Now, you should have paused. If you came back to the video, you should have found some expansions, series expansions for F and E. The typical one you find on Wolfram, for example, results in these two series, which I approximate to the first orders. So I will put an approximate sign. F of k is approximately given by pi half, this is the one you find typically, times 1 plus 1/2 quantity square times k, this k here, quantity square, plus 1 times 3 divided by 2 times 4, power of 2, k power of 4. Other terms, that's why I put the approximate sign there. Similarly, you will find that E of k can be approximated to the first few terms as pi half, 1, in this case minus 1/2 quantity square, k square, minus again 1 times 3 divided by 2 times 4 quantity square times k to the power of 4 divided by 3. This is the standard series expansion you find on Wolfram alpha, let's say, on Wolfram. Is this a useful expansion? Let's think about it for a minute. So if we go, eventually, we want the two loops to become a loop with the same radius, let's say small a, and delta is going to be small. So we go in the limit for capital A that goes to small a. This results in a k which approximately becomes 1 minus. So if you plug in small a, you get square root of a square, small a square. And if you do the calculation here, you will end up finding for small delta that this k becomes 1 minus for a small delta. So k approximately is equal to 1 in the limits we are interested in order to find the mutual inductance that it becomes eventually the self-inductance. In the limit that n becomes the self-inductance, this k is large actually, because the maximum value you can get here is 1. Okay, so if that is the case, this seems to be quite a little bit of a problem, because if we go back to these series expansions here, well, for the second one, actually it's not a problem, because we have 1 minus this quantity which is function of k squared, minus this quantity which is function of k to the power of 4. So there, this series, in that case, converges quite well, quite fast. That is, you can truncate it to this k to the fourth order and already gives you a reasonable estimate of the elliptic integral E of k. However, the other series, f of k, unfortunately features plus signs here and here. And so now we are summing up, and in fact, if you continue the series, there is always a plus sign. You sum up quantities which are close to 1, so you sum up very large quantities. And so this series does not converge very quickly. In fact, not only doesn't converge with the first 3 terms here, but even if you put several hundred terms or several thousand terms, it doesn't converge. It converges very slowly. That is, if you want to make a back-of-the-envelope calculation, but even not, if you want to do it numerically, you definitely do not want to use these two series expansions, which are the standard one. So a couple of years ago, when I decided to teach this Maxwell inductance in 342, I encountered this problem because I found online by Googling inductance of a loop some result which was function of a natural logarithm. We will come to that in a few minutes. And then I said, okay, so I need to be able to find this. So I want to find the solution to this by means of Neumann integrals, using this concept of attempting to find L from M, the self-inductance from the mutual inductance. So, and I didn't know that Maxwell actually did it, or I couldn't find it actually in the book of Maxwell, because I couldn't find the book of Maxwell. Okay, so I wanted to do that, and so one Sunday I started to work on this problem. And I said, okay, I managed to find the Neumann integral, as we've done, all the beautiful limits we talked about. I got to this point, and then I said, okay, now I need to solve this back of the envelope because I want to get something which is a simple solution like the one I Google for, and I decided to search for the series expansions of this FNE. And then I hit a wall because I find these two series expansions here in green which do not converge. So I said, what should I do next? Then it took me quite a while to find another series expansion which actually converges quickly. So it's a series expansion which is useful for the limits we are interested in here. A goes to A, small to big to small, and small delta. That is a k which is approximately equal to 1. So that's the beauty of this problem, is really that it took me quite a while to go back and find the references. And as it turns out, a physicist called Alexander Russell, I believe in 1912, wrote an article in which he discusses about another series which is distinct, different from this one, from this series. This other series actually is due to Legendre, and it gives the following result. The series is as follows. In the Legendre series, the one we're about to do here, f of k can be approximated as the natural logarithm. Here the natural logarithm comes and says, oh, okay, and then I started to be confident that this approach was correct because I saw the natural logarithm that when you Google for the inductance of a loop was there. So I said, okay, this must be the right path. Okay, so then I started to be more optimistic that my path, the path I was following, was proper. Of 4 times divided by k1 to be defined in a minute, in a couple of minutes, plus 1/2 square k1 square times the natural logarithm again of 4 divided by k1 minus 2 divided by 1 times 2. There are, of course, more terms, but I truncated, that's why I put approximately. Similarly, for e of k, this one gives 1 plus 1/2, without squaring it this time, k1 square, again to be defined in a minute, times the natural logarithm of 4 divided by k1 minus 1 divided by 1 times 2, which is just 1/2, whereas this one is just 1. Okay. This Legendre series is based on the following definition of k1. So k1 is the argument of this series. So more properly, we should write it here also as a function of k1. Actually, I keep it as a function of k because implicitly, it's more proper to do that, because implicitly what happens is that k1 square, which is the Legendre argument, is given by 1 minus k square, and eventually, of course, the original elliptic integrals are in k, so we want this relationship to k, so we keep it still as a function of k and k here in f and e respectively. Now, the beauty is that when we go in this limit, so when k goes to 1 minus, which is the case we are interested in here, then it so happens that k1 becomes approximately 0 plus, which is kind of nice. So this means that k1 is a small quantity, and these two series both converge very quickly. In fact, we can stop right there. We don't need, there are more terms, of course, in this Legendre series, go to infinite terms, but it's enough to use these few terms, and this will give a very reasonable estimate. Not a crude, but actually a very reasonable estimate for the inductance of a loop. And so the beauty is that by means of this series, we can do a back of the envelope calculation. We don't need a computer to do it. And in a few steps, we can find this mutual inductance. So the beauty is really to find the right reference, and this is very common in physics. You really need to find the right reference which helps your case. In this case, these limiting conditions here. Okay? With this, you're on the right path. If you use this, you will never find the right solution. This is the way to do it. Okay. Well, you will find it here only if you go for thousands of terms. All right. So how do we proceed next? The next thing we want to do is actually to use this expansion into this quantity up here. So we want to use this expansion exactly here. So we substitute it back, and we find a new expression for the mutual inductance, which I'm going to write down here. So m to 1, and let's keep it still for A and A different. In the next video, we're going to go in this limit, so that actually this m to 1 becomes L, the self-inductance. So this, now we need to say is approximately equal because this f and e will be approximated up to these terms by these functions. So it's not equal anymore, it's approximately equal to minus mu naught, still mutual, instead of self, A. Great. And now we need to do k times fk. So let's do k times fk. So we end up having k times the natural logarithm of 4 over k1 plus k times 1/4 here times k1 square times the natural logarithm of 4 over k1 minus, this is 1, so minus k from here again, minus k times 1/4 times k1 square times minus 1. So this is simply just minus 1. Now, the second line is going to be minus 2 over k times this same quantity. So we just substitute, we change it, there is a minus, so this k becomes minus 2 over k times the natural logarithm of 4 divided by k1. This plus becomes minus, k becomes 2 over k, 1/4 k1 square, natural logarithm of 4 divided by k1, and finally minus becomes plus 2 over k, 1/4 k1 quantity square. The next term, let me add it up here. So these I wanted to put it back to back because they are coming all both from F. And the one coming from E, let me add it up here for space reasons. So in this case, we're going to have 2 over k times 1, which is 2 over k, plus 2 over k times 1/2 times k1 square times natural logarithm of 4 over k1 minus 2 over k, because of this minus here, times 1/2 times k1 square, 1/2 k1 square times minus 1 over 2k. Perfect. Now we note that this last entry here, 2 over k minus 2 over k, 1/4, this one, of course, is 1/4 because I have 1/2 times 1/2, so it's 1/4 down here. So minus 2 over k plus 2 over k, 1/4, 1/4, k1 square, so these do cancel out. And so the final result can be eventually written here. Let's write it in blue as a final result. For m to 1 is going to be, of course, approximately, but the result of this calculation here is going to be, when we sum everything up, minus mu naught square root of a times two terms without the logarithm, 2 over k. So this 2 over k, which is somewhere here, this 2 over k, and there is another one which is minus without logarithm, is this one. There should be another term without this is logarithm, this one, which is minus 1/4 k1 square. And then there are 4 terms with the natural logarithm, so plus natural logarithm of 4 divided by k1, which multiplies 4 terms, k. Let's begin actually with, let us begin with k. That's exactly right. Then there should be 1, which is plus 1/4 k, k1 squared. And then there should be another term, which is k1 squared minus 2 over k, minus 2 over k. And the last term is minus k1 squared over 2k. Let me recheck if this is all correct. Minus mu naught square root over a, 2 over k, minus 1/4 k, k1 squared. These are the only two terms. And then the logarithm 4 over k1 has 4 terms, k plus 1/4 k, k1 squared, minus 2 over k, minus k1 over 2k squared, which comes from this calculation here. Exactly. Perfect. So this solution here, so let me highlight it, m21 approximately equal to this result here, is the first set of approximations for our self-inductance eventually, okay? So it's still a mutual inductance. So what we are going to do in the next video, we are going to rewrite this last expression here, and then we need to perform a Taylor series. So you see, I mean, this is quite complicated. So we started from a Neumann integral. We find out that this is solvable by means of elliptic integrals of the first and second kind, which have to be expanded, but not with the standard expansion, but with a Legendre expansion, which converges quickly for our scenario, which eventually is the self-inductance, which is the physics we need to keep in mind. We do that, and that's the first series of approximations. In order to further manipulate it, we need to make a Taylor series and remove higher order effects and manipulate that further to account for this concept, the physics of delta, and this will give the final result. So in the next video, we're going to start from this. That's it.